All right, so thin film interference is when you have reflection happening on the upper portion of a film and the bottom portion of a film. And it looks like this. You've all seen like a film of soap or something like that. Light reflects off of it and you get these cool colors. You get bright spots and dark spots. So here we have like an oil slick. That's also considered a thin film. If you have oil on top of water, it makes a very, very thin film, and then light reflects off of it. Some is reflecting off the top surface of the oil. Some is reflecting off the bottom surface of the oil. But to understand thin film interference, you have to know that there's two types of interference. There's what we call constructive interference. Now, constructive interference is when you have waves that are what we call in phase with each other. So the phase of a wave, if you're talking about the phase of a wave, you're either talking about, you know, the peak or the trough. So these two waves right here, these two waves are in phase with each other. So notice we have peak, peak, trough, trough, peak, peak. So they're totally together. If you have waves that are totally together like that, you're going to get constructive interference. And what's the result of constructive interference? Two waves that are in phase are going to add to each other and give a wave with a larger, what do you call that distance right in there? Amplitude. That's the amplitude of the wave. So it increases the amplitude and therefore the intensity of the wave. Now, destructive interference. Destructive interference is when the two waves that you're looking at are out of phase with each other. So this wave is at a peak. This wave is at a trough. Here we have trough, there we have peak. So what are these two waves going to do? At all points they cancel, and the end result is zero amplitude because they cancel perfectly. So we have constructive interference and we have destructive interference. All right, now here's what's happening with thin film interference. So we have this incident ray right here. So everybody look at this incident ray coming into this surface where the initial boundary is between air and oil. And then down here we have water. So we have three materials present. Now the thin film in this scenario would be the oil. The oil would represent the thin film. All right? Now, what happens is this. So you're already familiar with what happens here. So this incident ray comes in like this. Now, what happens at this first boundary between air and oil? Some of this incident light ray is going to reflect and go like that, but then some of that light ray is going to refract, and if you look closely right here, they don't really show the refraction. Period 1 was noticing that. It looks like it just goes straight in with like absolutely no refraction, right? In reality, it would refract towards the normal. They didn't do a very good job of showing that. But so the ray goes into the oil, refracts into the oil. Now what happens down here at this surface? It reflects, and probably some refraction too, unless you have total internal reflection there, if the index of refraction is high enough of the water. But you're going to get some reflection here, and then when it comes back to the oil-air boundary, it's going to refract out like that. Now, this person right here, I don't know if you realize this, but that's an eyeball. Some period 1 thought that was like 2 fingers reaching down or something. That's the person's eye. Now, this person is either going to see a bright spot right here where on the oil, or that person's going to see a dark spot. What will determine whether a bright spot is seen here or a dark spot? These two rays. If these two rays are in phase with each other, so in phase means they're both like they're doing the same thing. They're both together like that. If those two rays are in phase, it's going to be constructive interference. And what are we going to see right here on the oil? So you follow where she's looking, straight down like this. What are you going to see? Bright spot or dark spot? a bright spot. Now, what would have to be true in order for her to see a dark spot right here on the oil? The two waves would have to be out of phase. You guys follow me? So this is what thin film interference is all about. So the factors that are involved here. So here are the three factors that are involved. So number one, there's a phase change of a wave upon reflection if the reflection is at a boundary where the light ray is reflecting off of a medium with a higher index of refraction. Okay, make sure you're looking up here. This is super important. Put your phone away. Look up here. All right, so whether or not this person sees a bright spot on the film or a dark spot on the film depends upon whether these two rays are in phase with each other or out of phase with each other. So here's what you got to realize. Number one, there's going to be a phase change whenever a light ray reflects off of a medium that has a higher index of refraction. So for example, air has an index of refraction of 1.0. Oil is about 1.5. Water is about 1.3. Now first off, what do I mean by a phase change? A phase change is when a wave goes from a peak to a trough, or a trough to a peak. So this diagram right here, what this is showing is we have a ray, we have this wave that's coming in to this boundary here, and what it's showing is that N2, so N2 is this side and N1 is this side. If medium 2 has a higher index of refraction, there's going to be a phase change, which is what they're showing you here. So the wave comes in at a what? Peak, and when it reflects off, it's going to be at a trough. A phase change will only happen when the light ray is reflecting off of a medium that has a higher index of refraction. Does that make sense? Now, here we have a ray, a light ray that comes in, and it's reflecting off of a medium with a lower index of refraction. So this side is N1, this side is N2, and N2 is smaller than N1. So are you going to get a phase change there? No. The only time you get a phase change is when the reflection is happening at a boundary where there's a higher index of refraction. If it's a lower index of refraction, there's not going to be a phase change. Yo.
Wait, sorry, I just had a question. Why doesn't the light penetrate the water?
It probably does. They just didn't show that. It probably refracts into the water as well. Yep.
Can you explain that, like, in terms of the oil and water?
Yeah, that's what we're going to do. So, okay, so this ray right here. So this ray right here that I'm circling, did it undergo a phase change upon reflecting on the oil? Yes. This ray right here had a phase change. Now, did this ray experience a phase change? It did not, because at no point, if you look at this second ray that I'm putting a circle around right here, this second ray, at no point did it reflect off of a boundary that had a higher index of refraction. If you follow the ray down here, so it comes down into the oil and then it reflects off water. But what's the index of refraction of oil? 1.5. What's the index of refraction for water? 1.3. So that's a smaller index of refraction.
So if let's say, this oil had a lower index of refraction, then it would be a change?
If oil had a small, yeah, so if this were like 1.2, yeah, then there would have been a phase change. Exactly. Then both of them would have had a phase change. Right? But it doesn't. It's 1.5. Okay. So, keep in mind what a phase change does. A phase change takes a wave at its peak and instantly flips it to a trough. Okay? Okay, second thing you got to realize is that this ray here, this second ray that I'm circling right here, has traveled an extra distance. Hasn't it traveled an extra distance than ray number 1? So by ray number 1 is this guy. Ray number 2 is this guy. Ray number 2 traveled an extra distance right there. That extra distance is going to be important. We'll talk about that on the next screen. Okay, now number 3, and this was on the quiz this week, there's a change in wavelength inside the film. As the light ray goes from air into the oil, the wavelength is not going to remain constant. So I'll explain this at the end, but for right now, if we called this N1 and then the oil was N2, the wavelength in air is wavelength 1, wavelength in oil is wavelength 2, you can use this equation to calculate the wavelength in the oil if you knew the wavelength in the air. All right, so let's put this all together now. This last screen is going to make it come together, hopefully. Okay, so we're looking at a diagram of what happens. So here comes this incident ray. This incident ray strikes the boundary between air and oil. The rule for phase change is if the incident ray strikes a boundary that has a higher index of refraction, there's going to be a phase change. So will there be a phase change for this ray? So let's look at what happens. The ray comes in like this, strikes this boundary. Air has an index of refraction of 1. Oil has an index of refraction of 1.5. Will there be a phase change for this guy? Yes. So I'm going to put PC for phase change. This ray underwent a phase change. Now, in order for this ray to be in phase with the first ray, so let's call this guy ray number 1. We're going to call this guy ray number 2. What needs to happen in order for ray number 2 to be in phase with ray number 1? Well, here's what we have to look at. We got to look at the extra distance traveled by ray number 2. The extra distance traveled by ray number 2 has to do with the thickness of the oil film, which we're calling D. Now, we're going to approximate this. This is an approximation. We're going to call the extra distance traveled as this ray goes boom down to the water boundary and then back up to the air boundary. We're going to call the extra distance traveled 2D. It's an approximation. Is it pretty close? Yeah. If you look at like a really fancy like engineering textbook for physics, they get into angles and stuff. They start breaking it down to like cosine theta. It becomes a lot more complicated. But for purposes of this class, we make an approximation that the extra distance traveled by ray number 2, you know, it goes bam to there and bam to there. We're going to call that extra distance 2D. Now, here's where you got to put your thinking cap on. Realizing that ray number 1 underwent a phase change. A peak became a trough, or maybe a trough became a peak, but the wave literally flipped. In order for ray number 2 to be back in phase, what has to be true about this extra distance traveled to put ray number 2 back into phase? What would have to be true about the extra distance traveled? It's some multiple of a wavelength. If it were equal exactly to one wavelength, would that put it back into phase? No. It would have to be wavelength over 2. Or it would have to be 3 over 2 wavelengths, 1.5 wavelengths. Or it would have to be 5 over 2, 2.5 wavelengths. It needs to be a 0.5 multiple of the wavelength in order to get back into phase. Does that make sense? That's kind of the whole thing with thin film interference. Okay? Now, what if we wanted a dark spot down here? So somebody's eyeball is up here, somebody's looking down. What if we wanted there to be a dark spot instead of a bright spot? What would have to be true about the extra distance traveled? So only ray number 1 had a phase change. If we wanted this to be a dark region, what would have to be true about the extra distance traveled? It would just be a wavelength, or 2 wavelengths, or 3 wavelengths.
And that's so that they're out of sync, right? They're on the same phase.
Yeah, so if this is going to be a dark spot, then these two rays here have to be out of phase. You would need destructive interference. Okay? Now, the final thing to realize is that the wavelength in air and the wavelength in oil, is it the same wavelength? It is not the same wavelength. So let's talk about how you can find wavelength out. I want to derive that equation for you. So say we have air and oil. So air we'll call N1, and that's 1.00. And then the wavelength in air we'll say is like 500 nanometers. And then oil, we'll call that N2. Oil is about 1.5. So let's say you have this information, and you're trying to find the wavelength of light as it goes from air to oil. So you got this light ray, comes in like this, refracts into the oil, and you're trying to find the wavelength in the oil. So you can figure it out from these two equations. So index of refraction is equal to C over V, where C is the speed of light in a vacuum, and then we also know that velocity is wavelength times frequency. So here's how I make sense of this. Taking the first equation, take the first equation, solve it for C. So C is equal to N times V. Now, what do we know about C? Is it a constant?
Yes.
Yeah, it's the speed of light in a vacuum. So C is a constant. Now, if that's a constant, that means that N times V must also be a constant. So you can go N1 times V1 for medium 1 must equal N2 times V2 for medium 2. Then take this equation, plug it into velocity. All right, so we know that, so we go N1, that's going to be wavelength 1, frequency 1, equals N2, wavelength 2, frequency 2. Now what do we know about these frequencies? They're the same. The frequencies are the same, so this leaves us with N1 wavelength 1 equals N2 wavelength 2, which makes sense because as your index of refraction goes up, the velocity of the wave goes down, which means the wavelength goes down. But that is the equation from here. That's this equation for finding wavelength in a given medium. All right, but the big thing you got to get your head around, and it's not terribly complicated. The big thing to get your head around is like, all right, if you're going to see a bright spot, that means that these two rays have to be in phase. And you got to factor in when a ray reflects off of a medium with a higher index of refraction, you're going to get a phase change. But what's the second thing to factor in? The second thing to factor in is this extra distance traveled. The extra distance traveled can put these two rays back into phase, right? So you go, all right, extra distance traveled is 2d. If you want to put these back into phase, then that's got to be equal to wavelength over 2. That's the first possibility. What's the next possibility? 1.5 wavelengths. What's the next possibility? 2.5 wavelengths. It's got to be a 0.5 multiple. If you want a dark spot, if you want this to be a dark spot, then you want these to stay out of phase. So then you would say the extra distance traveled is just equal to a wavelength, and that would keep them out of phase.